Hey everyone, there's an old saying out there, and that is how do you eat an elephant? Well, the answer to that question is one bite at a time. And as with anything, if we're going to begin a long preparation or a long journey looking at the different technologies, protocols, and features associated with routing and switching in the version 5 format, we have to start somewhere. And I can't think of a better place for us to be able to start than looking at the concepts and precepts behind VLANs. VLANs and VLAN trunking are going to be the primary issues that we're going to want to make certain that we understand and know how to make operational as quickly as humanly possible. Why do I say as quickly as humanly possible? Well, we've only got so many hours that we have allotted to be able to take this exam. And this lab is arduous. And in the context of version 5, we're going to want to move past layer 2 reachability as quickly as possible so that we can dive into the meat and potatoes of IPv4, our routing protocols, redistribution, BGP, and all of the fun components. Now, I'm not saying that routing and switching isn't fun, i.e. the switching component, but it is in all actuality my least favorite of subjects inside the overall umbrella of the topics that we need to be able to cover. Now, when we start working with VLANs, we're forced to ask ourselves a number of questions. And the first question is why do we need VLANs? Well, the main idea here is that it allows us to obtain this idea of virtual segmentation. Now, we live in a time where there are entire disciplines actually set aside and devoted to this idea of virtualization. The data center track is a perfect example of virtualization taken to the extreme. But we have to recognize the fact in the context of our preparations for CCIE routing and switching version 5, we have had virtualization since the beginning of the track. We have virtual local area networks, or VLANs, which is going to be what we're talking about now. And very soon, we're going to segue into the IPv4, or the routing topic of virtualization, which is going to be virtual routing and forwarding instances. So this is nothing new to us, and it's obviously something that has taken hold and expanded as we start looking at these other disciplines. And what we want to do is focus purely on this routing and switching version 5 element. Now, when it comes to RNS v5, like I said, we need to be able to understand the principles behind VLANs. Now, I promised in the very beginning of this course that we would cover the theory and the component, and then we would move directly into the equipment. I don't want to have necessarily compound the two. So what I will do is in this particular portion of our presentation, let's stick to the theory, and then what we're going to do is we're going to dive right in and take a look at exactly what happens with this virtualized segmentation of layer 2 topologies. Now, we have to recognize how layer 2 operates. Remember, we use frames. All right, I don't want to rehash everything that we talked about in CCNP, but the main thing that we have to recognize here is that information is being sent throughout our layer 2 topology, and it's not necessarily sent in the most sensible fashion. Now, what do I mean by that? I mean that we have these scenarios, these mechanisms that allow our layer 2 environment to converge and create different topological graphs to ensure that we don't have any type of loops inside of our layer 2 infrastructure. Now, bearing in mind, we're not going to be talking about spanning tree protocol yet, which is the primary go-to tool that we have in RNS in order to be able to ensure that loop-free environment. It's still going to be incumbent upon us to have a healthy conversation talking about what layer 2 topologies look like. The idea here is that when we have information that we need to send, we need to do encapsulation. In order to do encapsulation in an Ethernet environment, we need to be able to obtain information associated with the layer 2 header information. When it comes to layer 2 header information and Ethernet, we're talking about MAC addresses, media access control addresses, 48-bit burned-in addresses that are actually physically assigned to our devices. And what we're going to do is we're going to find out that we need to be able to garner that information. And there's an entire technology associated to it called ARP, Address Resolution Protocol, that allows us to take a layer 3 IP address and resolve it to its layer 2 MAC addresses for the purposes of doing encapsulation and sending information across the line. Now, recognizing the fact that we have these frames and we need these MAC addresses, we also have to recognize the fact that we don't have any other method to be able to get information across our layer 2 infrastructure when it comes to obtaining information about things we don't know. ARP, Address Resolution Protocol. Address Resolution Protocol allows us to obtain information about that MAC address of our destination. Now, in order to be able to acquire that information, we need to be able to send frames that are architected such that we can get our request throughout our layer 2 infrastructure, and we do that through a process called flooding. Now, we'll talk about this in greater detail, obviously, but bear in mind, we flood multicasts, we flood unknown unicasts, and we flood broadcast messages. Now, again, recognizing the fact that we're going to do some poison reverse type of scenarios where we're not going to send information out interfaces that it was received on to mitigate this idea of creating layer 2 loops, that's one thing. But the other element here is that we have to recognize that the bigger our layer 2 environment, the more devices we have contending for our layer 2 infrastructure, the more possibilities we have of having less than optimal configuration in our switching deployment or our bridging deployment, whatever term you want to be able to use to negotiate that. So it's going to be through the creation of these VLANs that we can actually subdivide or parse our layer 2 infrastructure into different areas. Remember, in CCNA and CCNP, we studied that routers break up broadcast domains and switches break up collision domains. However, I have the capability of creating multiple broadcast domains through the utilization of this idea of VLANs. Now, these VLANs, as it says here in the presentation, provide scalability and also broadcast control access when I am working with multiple switches. Now, what do I mean by multiple switches? Well, if I'm going to take a switch and connect it to another switch, and I'm going to use a limited number of interconnections to be able to accomplish that, what I have to recognize here is that I need a special type of link. A link that's going to carry all VLANs, and we'll get into that. It's called a trunk, obviously. But what we're going to do is we need to also recognize the fact that as information gets moved across these devices, now what ends up happening is that I get a larger and larger layer 2 environment. If we take into account that the typical switch supports 24 connections, once I connect it to another device and I'm sharing a link or a trunk between them, now what I've done is I've almost doubled my capacity, minus the 2 ports that I'm using for my links. And again, it gets bigger and bigger and bigger. And the entire scenario can snowball. We can create an environment where we can run into problems associated with sending information. This whole idea of flooding. Because the bigger our layer 2 environment gets, the less efficient it is. Now, recognizing the fact that we can use VLANs to break up our networks into subnetworks or networks, no matter what term you want to assign to it, they're still virtual local area networks. Now what they're operating is they're operating in different isolated areas inside of our layer 2 infrastructure. The other component here is this last element, and that's going to give us, it gives us traffic flow management, because now based on VLAN, I can actually change how I route information across my layer 2 infrastructure, thereby obtaining capabilities like primitive or administrative load balancing. And also I have some security elements that are going to come with using these VLANs, because remember, once I set up a group of users inside of a VLAN, they are isolated from users inside of another VLAN or even the default VLAN. And in order to get information from point A to point B, I'm going to have to engage some type of routing device in order to get information to move through. And these are going to be the things that we're going to need and want to discuss as we start looking at how we operate with VLANs. Now, I mentioned a VLAN is basically just a group of users operating in their own network segment. And what can we actually use to comprise VLANs? Well, VLANs are made up of hosts, switches, switch ports, and VLAN protocols. Now, VLAN protocol is kind of an oddball or an off-the-wall term, because in all actuality, what we need to do is we need to ensure that if I'm going to use this concept that I mentioned earlier about a trunk, and I want to send traffic across that trunk, remember, that's one or a bundled pair of interconnected links between switches. So if I'm going to send information for VLAN 1, VLAN 2, VLAN 3, and VLAN 100, when I put it on that individual cable, that link between my 2 switches, how do I ensure that the information doesn't get all jumbled up? How do I make certain that VLAN 1's traffic is isolated, separate, and identifiable from VLAN 2? And that's going to be this idea of these VLAN protocols. The VLAN protocols, or encapsulation protocols, come to us in 2 flavors in the context of the CCIE routing and switching exams. Typically, we have ISL, which is going to be inter-switch link, Cisco proprietary. Also, not part of version 5. And we'll revisit that, so it's not part of the V5 blueprint. Now that only leaves one other protocol that we can use in order to be able to handle this information, and that's going to be the idea of 802.1q. 802.1q is an industry standard protocol that allows me to be able to identify traffic across that link. And therefore, I can guarantee that VLAN 1, VLAN 2, and VLAN 100's flow of frames across that link are going to be separate and maintained and isolated to where they're not going to be able to be merged. Now, recognizing exactly how this happens, what we want to do is understand some of the component pieces to this equation. And that's going to be the fact that we have ports. Everything that we talk about in the context of a switch is normally going to be discussed from the point of view of ports. And when it comes to ports, we have to recognize that we have different configurational capabilities on a port. We have default configurations based on switch. We also have default configuration based on whether or not we're connected to a host or whether or not we're connected to another switch. So recognizing this, it really boils down to these four components, and one of these components is outside the scope of the context of the version 5 lab. Now, when we look at this, the main element and the most common port type that we're going to be working with is going to be access ports. All ports, so ports will automatically be part or be configured as access ports if we're not connected to another switch. Now, we'll have to recognize that we have to understand that there's going to be operational behaviors that are varying from platform to platform and from iOS to iOS. Now, when we come in here and we start setting up, the day I get my switch, I take it out of the box, I put it on my table, I plug cables up to it, and I start doing my configurations. What I'm going to find is every interface on that switch is going to be participating in a VLAN that I didn't create, a VLAN that I'm going to have by default. That's why it's called the default VLAN, and that's going to be VLAN 1. Now, we're going to find that we're going to have numeric representations for these VLANs. We can also assign them names and some other elements. But the main thing that we need to recognize here is that we have a range of addresses that, or numbers that we can use to represent this idea of VLANs for the purpose of allowing our encapsulation protocol to do its job. Now, the moment we start actually encapsulating traffic, that means that we're operating in a port mode trunk. So that means we are encapsulating information. And the only protocol that we have that we can encapsulate in is the idea of .1Q, a colloquial term used to represent 802.1Q. Now, when we look at this, we have two different ways that we can operate our trunk ports. We can do it either statically, or we can configure it to where they're going to be allowed to operate dynamically. Dynamic negotiation of trunks is going to use a special protocol that we're going to spend quite a bit of time talking about called DTP, Dynamic Trunking Protocol. Now, it's going to be through the use of DTP that we can exchange information between our switches, that are going to allow them to be able to negotiate links under certain circumstances. And as CCIE routing and switching candidates, we need to understand each and every one of those possible permutations and all of those circumstances in order to be able to ensure that we can get our Layer 2 environment up and operational, like I said, as quickly as possible. Now, looking at how the system is configured, it's also going to be incumbent upon us to understand exactly what's happening with these ports. So let's start taking a look at them from the top down. We'll begin with the access port. The access port, as configured, is going to be a port that's going to be connected to a host. Now, by a host, what do I mean? I mean a computer. I mean a router in this instance, something that is not going to be participating in my Layer 2 infrastructure. Now, under some circumstances, it could be, say, for instance, a wireless access point. But the main thing that we want to look at here is that our access ports are going to allow us to connect to hosts, and most predominantly, the key differentiator between an access port and a trunk port is going to be the fact that an access port is only going to be aware of one VLAN. Now, that's not even really a true statement. What's going to happen is an access port can only be a member of one VLAN. The host that's sending information, that's sending these Layer 2 frames, is completely and utterly ignorant of any Layer 2 or encapsulation or VLAN infrastructure that may be running in our Layer 2 domain. So if I have a router and I'm going to send traffic and I want that traffic to be designated as VLAN 2, the router is never going to know anything about VLAN 2 unless I go in and configure it. It's not necessary. It's simply going to send its frame down to the switch, and on the switch port where the frame arrives, that's where we're going to be applying any type of tagging. Now, this is going to call into a point of view two different terms, tagged and untagged frames. An untagged frame in 802.1Q or .1Q is referred to as a native VLAN. So it's sent in its native format, which means untagged. Now, the idea here is that if I have a device, what I can do is I can send information that's untagged. The switch is going to apply the tag, and then it's going to allow it to be kept and maintained and isolated inside the context of the layer 2 domain until such time that it exits the interface where the tag is going to be removed. So as we take a look at how this entire process takes place, it's important for us to understand just a handful of elements before we can move on and start talking about some of the other port types. Now, like I said, hosts are completely unaware of any type of VLAN encapsulation. And that's a good thing because it's less configuration on our part. All we have to do is just configure the port facing the host to place it in a VLAN. Switch port, and then we assign the mode access or switch port access VLAN, and then that's pretty much done. And again, we'll walk through all of this on the equipment, but first what I want to do is get through the theoretical discussion. Now also, recognizing the fact that we have all of these ports, when we go through and set up this idea, the access ports can only be assigned to one VLAN. That's the predominant idea here. Access ports belong to one VLAN. Averse to trunks. Now, trunks can belong to multiple VLANs, or all VLANs for that matter. So keeping in mind, if I have R1 connected to SW2, connected to SW3, connected to R3, what's going to happen is remember, I'm going to send my traffic from R1 untagged. Now, the moment that frame arrives on, say, Fast Ethernet 01 on SW2, what's going to happen is if there's appropriate configuration on that interface, we will actually apply the tag. We'll talk about the nature of tags very shortly. But then what's going to end up happening is that tag is going to be associated with that packet as it traverses the layer 2 domain until such time that it leaves the layer 2 domain to be delivered. And then what's going to end up happening is the VLAN information, what we're going to refer to as the VLAN ID, is going to actually be stripped off, and the packet is going to leave towards its destination in its native format. So again, there's not a lot of moving parts to it. There's not a lot to understand, but it's still going to be really, really pivotal that we understand what takes place in our layer 2 environments, especially when it comes to this idea of our access ports and our trunk ports. Now, a trunk port boils down to the fact that, like I said, it can carry more than one VLAN traffic, or the traffic for more than one VLAN. There we go. That's probably the best way to say it. Now, when we look at this and we start setting it up, what we have to recognize is that there's going to have to be some tool or some method that's going to allow me to do that. And we mentioned that. We mentioned the ISL and we mentioned the .1Q trunking, which was what we were considering or calling our VLAN protocol or our VLAN encapsulation protocol. That's going to be the protocol of choice that we're going to use to ensure that we can keep our traffic isolated from each other. Now, recognizing the fact that this goes through, like I said, the trunk ensures that I can carry multiple VLAN information simultaneously. So what I'm going to find here is if I look at a link where I have, say, R1 connected to SW1, SW2 connected to R3, where I'm talking about is right here. I'm talking about the link between these two devices across my trunk. The trunk is going to allow me to carry traffic for different VLANs. So for instance, if I had another arrangement here where I had, say, R4 and R5, and I wanted to make certain that I sent R5's traffic across this link and simultaneously had the capability of sending R1's traffic across this link, I need to be able to ensure that I can protect the black frames from the green frames. Now, that's just a visual example. So this could be black, could be VLAN 2, and yellow or green could be VLAN 100. It doesn't matter. And it's through the idea of being able to take a piece of information and insert it into the frame that I'm going to make certain that I maintain this isolation between my different traffic flows with regards to frames associated with different VLANs. Now, the other part of this that we need to really pay attention to is the fact that the system allows us to operate in one of two modes. We can operate as a static trunk or a dynamic trunk. Now, dynamic brings with it some additional baggage. We have a protocol called DTP that we're going to spend some time talking about, and I promise we're going to spend a lot of time playing with it on the equipment. But the idea behind DTP, Dynamic Trunking Protocol, is it's going to be a process that's going to run across the trunk on the individual interfaces when we are operating in an automatic or a dynamic trunking mode that's going to allow the system to exchange information so that it can agree on the VLAN encapsulation protocol that we're going to use. Now, why did I bring up ISL? Well, I brought up ISL because the majority of switches that are older, 3560s, some of the other devices, are going to automatically use this idea of dynamic configuration, and they're going to come up by negotiating an ISL trunk. I merely want to make us aware of the fact that ISL exists, and also point out the fact that if you bring a trunk up and they say to use the .1Q protocol, then what's going to happen is automatically some of these devices may not actually come up through the dynamic negotiation to satisfy the particular criteria of a question. So I just want to make certain that we're aware of these. We will see it when we get into the actual gear, but keeping in mind that it's through this idea of exchanging information that we can actually bring up these inter-switch links. Inter-switch links is also just another name for a trunk. Now, when we go in and we start doing the configuration, what we also have to recognize is if I wanted, I could run a trunk up to R1. Now, the thing that you need to understand is that if I'm going to do that type of configuration, there are some efficiencies I want to make certain that we understand right out of the gate. So what does this imply? Well, it means I can run a trunk up to a router. Now, that means I can carry VLAN information. But can a router support VLAN information, separate VLAN information? And the answer to that question is yes. Routers have the capability of being able to run .1Q encapsulation on their physical interfaces through the creation of something called an actual subinterface. And we'll look at how that's doing. And this is actually going into how I can get routing between two VLANs through the use of an actual router, which is going to be a concept called router on a stick. Now, recognizing exactly what's going on here and knowing how to set it up and make it work is one thing. Understanding how it's going to operate and make it efficient is another. Now, the reason I'm employing this or I'm stating this is that by default, DTP is going to run on that trunk unless I go in and turn it off. And we'll talk about how to disable it later on. But the main idea here is that switches speak DTP across trunk links and routers don't. So when we look at this, it's important for us to understand that dynamic trunking protocol will not be running on our routers. So if we were to be asked a question to make certain that we minimize traffic when and where possible or reduce the number of unnecessary frames, we may find ourselves in a situation where we're going to want to restrict VLANs that can travel across the trunk going towards the router and also disable this idea of DTP, dynamic trunking protocol. Now, with that being said, let's take a look at DTP. DTP, again, two modes. We have desirable and we have auto. Now, the primary difference between the two is slim. They both want to form links. Desirable will go so far as to initiate the formation process. Auto will just simply sit back and wait for someone else to initiate. So think of it as, taking a shy guy out to a club or out to a bar. All right, it's very difficult then to get them to initiate a process, but we all know that they really want to get out and meet people. Well, the idea here is the same in the context of DTP. The desirable mode is going to be the gregarious, the outgoing method. It's going to be, okay, all right, I want to negotiate a trunk and let's do it now, and I'll start. So it's going to be the first person to put the hand out. We're also going to have to recognize that auto is going to be a passive method. It wants to negotiate. So if someone comes up and initiates the conversation and tries to form the trunk link, then it's going to actually allow that to happen. Now, the main thing we also want to understand is when it comes to the gear, we're going to take a look at these DTP messages that are going to be exchanged between the devices using our diagnostics tools. Like I said in the very first portion of our introduction, it's going to be exceedingly important that we understand everything there is to understand about all of the tools and all about the normal operations of these protocols. So it's going to be important for us to see Wireshark traces on DTP negotiation. It's going to be important for us to see BPDUs, Bridge Protocol Data Units, being exchanged between switches in normal circumstances, because unless we know what they look like in normal circumstances, how can we rely on our skills to be able to isolate a non-functional or an improper or mismatched configuration? So again, just stepping into this, what we need to recognize is, like I said, DTP, Dynamic Trunking Protocol, is the go-to tool of choice for this idea of negotiation. Actually, I almost wrote auto negotiation. Negotiation comes in desirable, which is going to be the mode that's going to go out and try to initiate a link, and auto. Now, between DTP modes, this is it. But we also have to recognize the fact that, like I said, routers do not support DTP. So in other words, the dynamic trunking protocol cannot be used to bring up a connection to a router. Now, I mean, I could go so far as to say host, but we need to recognize that there are network cards, some of the Broadcom cards, that can run .1Q, and they could actually bring and form a trunk. And you could even use application software to be able to emulate VLANs. I mean, not necessarily a good thing, but it is capable. So in the context of what we're talking about, let's just stay focused on routers, because a router is going to be the main element that I'm going to use in order to be able to simulate hosts in the context of the CCIE routing and switching exam. Now, like I said, ISL, inter switch links. Cisco proprietary, not on the exam. In fact, this should be a big red X instead of a big green check mark. But what I do want you to understand is how it operates. It operates by actually inserting or re-encapsulating the originating frame. And it's going to do that using a 30-byte ISL frame, and it's going to use a 4-byte trailer that it's going to assign to the end of it. So it's actually re-encapsulating it, and it's adding this idea of, well, excuse me, it's going to be 26 bytes and 4 bytes, adding up to a total of 30. I keep wanting to make it bigger than it really is. But the idea here is that we've created a frame that's substantially larger than our original frame. One of the reasons is it's really fallen out of vogue. The other thing is it was created by Cisco to try to beat .1Q to market with regard to being able to communicate information about our VLANs. So the idea is that it served its purpose early on. It was part of Cisco's negotiation all the way up until just recently, and now Cisco's moving away from it. And like I said, by virtue of the fact that it's a default configuration, I just simply want us to understand what's happening if we see this idea of ISL rather than .1Q. Now, looking at this, it's also important for us to understand how the big boy works. .1Q. 802.1Q is an industry standards-based protocol, and it's super simple. All it does is insert a tag. It inserts a tag on the frame, and the tag basically has VLAN 4 written on it, VLAN 100, VLAN 200. Now, obviously, it's not a tag, and it's not an actual numeric representation, but it is going to be, like I say right here, it's going to be a 4-byte header. And that 4-byte header is kind of going to be shimmed between the MAC address and the ether type field in our frame. Now, the moment that this 4-byte header is inserted, now I know that frame is associated with the VLAN that is basically contained inside of that 4-byte header. Now, this is actually made possible through a process that really was referred to as 802.1P. 802.1P, an industry standards protocol, gave us the 802.1Q tag. Now, when we look at this, inside the context of that header, we can see that there's some other information. For instance, we have the tag protocol ID. The tag protocol ID is going to list an ether type of 0 by 8100. Now, the moment I see that, I know that I'm looking at a .1Q frame. And our sniffers are going to reveal that when we look at our Wireshark configuration. Two other key elements that we're going to need to know about. One we're not going to talk about until we hit QoS, and that's going to be the 802.1P priority bits. The 802.1P priority bits give me 3 bits in order to be able to assign a class of service value. Class of service is a quality of service mechanism used at layer 2 that is going to be employed on my trunks or my inter-switch links that's going to allow me to provide traffic preferential treatment based on COS. Now, it's going to be an actual 3-bit field, so that's going to be 2 times 2 times 2, which gives me the possibility of having 8 results, 0 to 7. So as I go up the chain, 7 is higher, so it's going to have a better priority than 0, which would be scavenger or next to nothing. So again, we'll talk about that in the confines of quality of service mechanisms when the time comes. But the other element here that's really important to us is this VLAN ID. The VLAN ID is the 12 bits of information that is used to express the VLAN number. And if we were to go through here and take 2 to the 12th power, what we're going to find out is we're going to have 4,096 possible permutations. Now, that's oddly enough the maximum number of VLANs, or the maximum VLAN number that's supported in the context of our Catalyst devices in the confines of the routing and switching exam. So when we look at how this is all implemented and how this all comes together, keep in mind there's going to be explanations, theoretical components and explanations that are going to allow us to have a better understanding of why things are taking place. And if we understand those, it's going to be easier for us to keep these things clear in our mind when we're sitting at the console. Now, I tell students time and time again, I'm a firm believer in the fact that CCIEs are made here. All right. You may hear people talking about learning by lab and that is a dangerous scenario if all you want to do is sit down and bang on a keyboard and just type in commands and do technology labs or mock labs over and over and over and over without a firm understanding of the operational theory that allows all of this to work. So if you cannot explain any of these processes as exactly that, a process or a procedure, you don't fully understand the theory behind what it is you're implementing here at the keyboard. But if you have that mental image, then when you go to the keyboard and you're actually doing your labs, what you're doing is you're submitting that knowledge into the back of your mind, and you're taking something that's just going to be in a theoretical construct, and you're assigning muscle memory to it. That's why I'm such a huge proponent of labs. That's also why I'm a huge proponent of making certain that we separate theoretical from the command line. Now, obviously, there's going to be some bleed over from theory to the command line, but what we want to do is we want to be able to knock out everything that we need to know about it from a theoretical point of view, and then go to the keyboard and lab the living daylights out of all of these technologies when and where possible. Now, like I mentioned, .1Q brought with it this idea of tagged and untagged traffic. Where the untagged traffic is called the native VLAN. So when a device or a host sends a frame to a switch, it has no information associated with it other than just the original payload. There's no header, there's no information assigned to it. It's just the layer 2 information associated with what's necessary to allow the layer 2 frame to reach its destination. But once it comes into the switch, that's where we have the option of going in and assigning a VLAN ID. Remember, we talked about inserting that little marker there between the MAC address and the ether type field, such that we can make certain that now that we can keep that traffic separate from other devices' VLAN traffic. Now, when we look at this and we actually just take the opportunity to just step into it, what we have to recognize is .1Q outlined a characteristic, like I said, called the native VLAN. Now, the native VLAN is going to be untagged, even between switches by default. So we're going to have traffic that's going to be traveling or traversing across our ISL links, our inter-switch links, which are going to be .1Q in the context of this lab. And those frames are not going to be tagged. So what ends up happening is we have a scenario where we can encounter something referred to as a native VLAN mismatch issue. Now, the main object to understand here is that native VLAN traffic has no 802.1Q tag inserted. So when a packet, or when a frame arrives on a switch port, it has no tag. So it's untagged. Now, the moment I attach a tag to it and send it across, what's going to end up happening is that if that tag is not VLAN 1, or whatever the default VLAN is, VLAN 1 being the default by default, excuse the term, but the main object here is that as this information gets moved through our infrastructure, we have to understand that VLAN 1 is really important to us. Because VLAN 1 is going to be significant because VLAN 1 allows so many different control plane mechanisms to operate. It's going to be how we communicate BPDUs in the context of spanning tree protocol. It's going to be how we use CDP, Cisco Discovery Protocol, the tool that we have available to us to help us identify and map out our entire infrastructure based on a neighbor-by-neighbor link relationship basis. So when we go in and we look at this idea of VLAN 1 cannot be overemphasized. Now, like I said, VLAN 1, or the native VLAN, VLAN 1 by default, has no 802.1Q tag inserted. Now, when we can set this up, if I have SW1 connected to SW2, and I'm running a link between them, that is a trunk, and I choose to allow the native VLAN to be untagged, so long as the two devices agree on the identity of the native VLAN, we have absolutely no problems. However, if this side thinks VLAN 1 is the native VLAN and this side thinks VLAN 10 is the native VLAN, then what we do is we encounter a scenario where our native VLAN mismatch exists. And what we're going to find here is that both spanning tree protocol, when we talk about it, and CDP protocol, which we're going to talk about very soon, are going to be the mechanisms by which the system is going to identify this issue. Now, once this issue has actually been identified, what we're going to find is that our spanning tree protocol is going to actually block the native local traffic to keep this situation from occurring, and this situation has a special name. It's called VLAN hopping. VLAN hopping is a way where if I was a third-party attacker, I could get a switch from eBay, and if nothing was done, there was no security, no implementation, I could simply plug the VLAN in, and what I could do is I could create a VLAN mismatch error such that I can actually start capturing information about the infrastructure. So the main point here is what we're going to do is, ideally, we're going to be picking a VLAN to use for our native VLAN communication. But what we have to recognize is it's not just as simple as that, because VLAN 1, no matter what we do, is always going to be used to carry certain control plane traffic across our links. Now the idea is that we do this simply because DTP and BPDUs are going to need to run across the native VLAN to ensure that we're going to remain and be compatible with other vendors' equipment. Because, I mean, not every scenario that we run into in the field is going to be a pure Cisco deployment. Now, I want to highlight some of the topics that we had talked about, because one of them was probably the most important element that we have available to us, and that's going to be the idea of VLAN IDs. Now, a VLAN ID allows me to communicate information about my VLAN. So what is the identity of my VLAN? I have a 12-bit field, 2 to the 12th power, gives me the capability of having up to 4,096 possible VLANs. Now, by default, we've already mentioned the fact that VLAN 1, let me grab a pen here, VLAN 1 is the default VLAN, which means it is going to be untagged by default. Now, that doesn't mean that it has to stay that way. And we also need to understand what VLAN 1 does for us. So like I said, every interface on a switch is going to be a part of VLAN 1 by default, unless we interfere with that process. The other thing that we need to recognize here is that the default VLAN can be changed, and anything that can be changed can be messed up. Remember, it's necessary and essential for us to make certain that we have a same native VLAN configuration on either end of a link. Because if we don't, we can actually run into that mismatch scenario where spanning tree can actually bring our ports down. And again, we'll talk about spanning tree. Like I said, sometimes we have to put the cart before the horse. So some of this lecture may make more sense after we've discussed spanning tree. But the other thing that I want to make certain that we recognize here is that VLAN 1 does some very special stuff for us. It carries control plane traffic. Now obviously it can carry forwarded traffic, but its most important role is the ability to be able to carry control plane packets or frames for VLAN trunking protocol, Cisco discovery protocol, port aggregation control protocol or port aggregation protocol, spanning tree protocol, and DTP protocol. Now, recognizing this, I mean, I just said an alphabet soup of abbreviations that you may or may not be familiar with. And like I said in the introduction of this course, we're going to cover everything from the basics all the way up. So yes, there will be detailed explanation as to what each of these protocols are and what they do for us. They will be discussed in their individual sections. But it's important to understand that these control plane mechanisms, these control messages, are going to be in VLAN 1. Now, by default, VLAN 1 is going to be untagged because it's going to be our native VLAN. But what happens if we change that? What if we go through and say, I want VLAN 1 is not going to be my native VLAN. My new native VLAN is going to be VLAN 100. Well, what you need to understand is that VLAN 100 will not carry these control plane mechanisms. They're still going to be carried in VLAN 1. However, by virtue of the fact that VLAN 1 is no longer the native VLAN, that means that all that traffic will be sent with a tag. So it's going to have an 802.1q tag. Now, this is important. This is exceedingly important, because what we're going to find out here is I have the capability of going in and creating a list that's going to say who can, or what VLANs can and cannot be communicated across a trunk. Now, what happens if I go in and say I want to remove VLAN 1? Does that mean that puts an end to this control plane traffic that's so important for me with regard to these other protocols that we have yet to discuss? No. Because what's going to happen is if I go in and I remove VLAN 1, or any other VLAN for that matter, first of all, removing a VLAN from a link like that or a trunk is called minimization. Removing VLAN 1 is called VLAN 1 minimization. I mean, it's not too hard to remember that one. But the idea is that if I remove it from the trunk, I'm removing it for the purposes of forwarding data. It's not going to forward data frames, but it is still going to be sending the VTP, CDP, PAGP, STP, and DTP messages, just like it always would. So the main thing that we need to understand here is that I have the capability of changing my native VLAN to another VLAN, but it's still going to be the job of VLAN 1 to carry all that control plane information. If I've changed the native VLAN to like VLAN 100, VLAN 100 will be untagged. And it needs to be untagged on both ends of the link. Doesn't necessarily have to be VLAN or untagged on all links, just so long as each end of the link or both ends of a given link agree that it is going to be the untagged or the native VLAN. Now, the other part of this is if I remove VLAN 1, I'm removing it just for the purposes of forwarding traffic. It's still going to allow me to carry and send the information associated with these control plane mechanisms that we've been talking about. Now, the last element before we finish this particular portion of our theoretical conversation is going to be referred to as the VLAN allowed list. The VLAN allowed list is where I can either allow or disallow specific VLANs on a trunk-by-trunk basis from sending frames across these interswitch links that we've been talking about. These .1q flavored interswitch links, but they're still interswitch links. They're just not running the ISL protocol. Now, when we look through here, like I said, anytime I use this method to remove a VLAN from a trunk, it's called minimization. If I use it to remove VLAN 1, it's called VLAN 1 minimization. Now, also, it's important for us to understand that if I remove it, it's still going to be sending that layer 1 information, the layer 2 information for the control plane mechanisms. So with this being said, it's time for us to dive out of the theoretical lecture and let's hop right into the gear and we'll start working at the command line. I'll see you guys there.